Hi everybody, my name is James Burnett and I'm going to be going over Lab 1, which is the charge tape lab. So, the first thing I want to go over is the objective of this lab, and that is firstly to create a model of two pieces of charged electric tape and observe how they interact with one another, and then observe how the electric force can counteract a gravitational force acting on the tape. Then we also want to estimate the net charge on each piece of tape and understand how electrons are transferred from something to something else. And the importance of this is to understand how to apply the electric force and Newton's second law to understand how charges, and specifically the electric force, interacts between charges of different nature. So key concepts for this lab are Coulomb's law, which is the law governing attraction and repulsion of different natures of charges, and other concepts that we need to be familiar with are the electric field, gravitational force, Newton's second law of basically just net forces, and then lastly, Newton's third law about equal and opposite forces. So, a couple things we need to go over really quickly. Firstly is how to make a piece of charged tape. So the very first thing you're going to do is put a piece of 0.2 meter pieces of tape onto a table sticky side down, and then you're going to get another piece of 0.2 meter piece of tape and fold one end underneath slightly to create a U-tape. You're going to place the sticky side of that tape down and then rip it up, and then you have a piece of charged tape. Then we're going to be determining the charge of the tape by firstly holding our hand near one and observing what happens with it. Then we're going to have two pieces of charged tape and put them together and observe how they interact. And lastly, we're going to rub a plastic pen on cloth to give it a negative charge and then hold it near a U-tape to determine the charge of the actual U-tape. So then we're going to be going ahead and determining the amount of excess charge on it, or the amount of charge missing. So what we're going to do is place one piece of U-tape on top of similar height objects. I use books. And then we're going to hold a piece of U-tape underneath that suspended U-tape and bring it closer until it begins to float. Then we're going to record the distance when this floating occurs. So, a few more assumptions that we need to make. We're going to ignore air resistance on this. We're going to treat each piece of tape as if it's a point charge to simplify calculations. And then lastly, we're going to assume that the U-tape has a uniform charge distribution and has the same amount of charge, just assuming that they're identical. So, the observations I made were that the U-tape and the hand had an attraction. That means that the U-tape is charged. The U-tape and the U-tape repelled one another. That means they have the same charge. The U-tape in the book, like how it would be expected, attracted one another. And then lastly, the U-tape and the negatively charged pen strongly attracted one another. So, what conclusion can we draw from this? Firstly, the U-tapes are charged and that they have the same charge, and we can base that off of the U-tape repulsion. Secondly, the tape must be positively charged due to the attraction of the negatively charged pen. And then other questions that we need to go over is what would happen if the charges were flipped? Now, protons are negative and electrons are positive, and the short answer is nothing would change, because any negative charge on the pen would switch to positive, and any charge interaction with the positive charges on the tape would still occur when they're negative. And then it's important to handle the charge tape as little as possible, because our skin is a very good conductor, and we'll just go ahead and steal the charge from the actual pieces of tape. So going into our data, firstly we have the length of our tape, the mass of our tape, and then I got my distance by doing the average of 3 trials. And then from that data, we can go ahead and calculate the magnitude of the force due to gravity. And then from there, we have to go ahead and apply Newton's second law of basically summing forces. And we find that the electric force is opposite in magnitude to the gravitational force. So now that we have our electric force, we go ahead and look at Coulomb's law, which is 1/4 pi epsilon naught multiplied by the charge of the tape squared, since we're assuming they're identical, divided by the distance between those charges. We rearrange that equation and go ahead and crunch the numbers, and I got 6.07 times 10 to the negative ninth coulombs for my charge. Then from there, we're going to calculate the deficiency from the tape, and that is simply dividing the known charge now, divided that by the charge on an electron. From there, we're going to go ahead and get the atoms of the atoms, and what we're going to do for that is calculate the surface area of the tape and divide it by the area of the atoms. And once you get that, you go ahead and calculate the ratio of the atoms to determine the deficiency of electrons due to this being a positive charge, in which case I got 1 to 1.05 times 10 to the 7th atoms. Lastly, for my computational model, I went ahead and basically organized my tape as 2-point charges, one blue and one red, the red one being the higher one that's suspended by the books. And then I have two forces shown by the 2 arrows. The yellow force, or the yellow arrow, is the electric force, while the green arrow is the gravitational forces. As you can see, they are equal in magnitude, but in opposite directions. So it leads to a net force of 0. All right, thank you guys so much, and have a good day.